Hi everyone. In this summary lecture, we will see what is the equivalence relation, what are the equivalence classes. Equivalence relation is very important in computer science, also in mathematics. What is equivalence relation? Equivalence relation is basically a relation which is reflexive, symmetric, transitive. So you have a relation on set A. So let's assume this is your set A. On this set A, you are defining a relation R. If this relation R has all these three properties, then we will say that it is an equivalence relation. These three properties we can call them RST property, reflexive, symmetric, transitive. Okay, RST. So if a relation on set A satisfies all these three properties, then we will call it equivalence relation. What is the idea of equivalence relation? So for example, just read this relation. X and Y have same color. Okay, so let's assume on set of people people. Okay, so let's assume on set of people or on set of toys, you are defining this relation that X is related to Y if and only if they have same color. Then you can clearly see that it is reflexive. Okay, because X and X, they have same color. It is symmetric also. If XY have same color, then YX also have same color. And also this is transitive. If XY have same color, YZ have same color, then XZ also has same color. So I can say that this is reflexive, symmetric, transitive. So this relation is definitely equivalence relation. Okay, so this type of relation are basically equivalence relation. You can notice we are saying X and Y have same color. Okay, X and Y have same color, so here color is same. So here X and Y are equivalent in terms of color. X and Y are equal in terms of color. Okay, look at this. X is equal to Y. You can clearly see this is reflexive because X is equal to X. This is symmetric, this is transitive. So this is also equivalence relation. Okay, here both X and Y are same, basically they have same value. So here I can say that X and Y, they have basically same value. Okay, here they have same color, here they have same value. What about this? X and Y have same shape. Again, this is reflexive, symmetric, transitive. Okay, so this word same shape. Similarly, if you look at this, X and Y have same, they have the same area, they live in the same area. This is also reflexive, symmetric, transitive. So this is also equivalence relation. X and Y are programs that produce the same output. Okay, so again, this is also reflexive, symmetric, transitive. You can just check it out. Okay, this is all these three properties are satisfied. So this is also equivalence relation. So you can notice one thing, that in the equivalence relations, this word you will see there is some kind of equality. There is some kind of equality, like maybe they are same value, maybe they are same color, same shape, same area, same output. Okay, so in the equivalence relation, there is some kind of equality. So in the equivalence relations, you can clearly see that there is some kind of equality that is involved. Like, okay, same value, same color. So this type of thing you will see. X and Y are related if they have same value. X and Y are related if they have same color. X is related to Y if they have same remainder when you divide by M. They have same shape or same length. So in every equivalence relation, whatever equivalence relation you take, there is some kind of equality that is involved. Here equality of color, here equality of value, here equality of shape, here equality of remainder. Okay, so there is some kind of equality that is involved in the equivalence relations. Okay, so you can clearly see an equivalence relation has some kind of equality involved. Okay, there is some kind of common trait, there is some kind of common properties that elements have. Remember, this is not a formal definition, this is just idea. Okay, so for example, let's assume your base set is set of all shapes. Okay, so we have a base set, let's assume that is set of all shapes. On this set S, let's assume we are defining a relation R on this set S. On this set S, we are defining relation R. What it means? It means this relation R is from S to S. Okay, or I can say this relation is basically subset of S cross S. Okay, all these things are same, you know. Okay, so anyway, the point is that we are defining a relation on S, and I am saying that this relation on S we are defining like this. We are saying that X is related to Y if and only if X comma Y have same shape, have same shape. So you can clearly see that this type of relations are this type of relations are equivalence relation. Okay, this is a relation, and we are saying X is related to Y if and only if they have same shape. Okay, so you can clearly see that. Okay, so for example, these three, this and this, they have same shape, and this they have same shape, and this they have same shape. Okay, so you can notice that. Okay, these two are related, this is related to this is related to this. Okay, similarly, okay, all these three are related to each other, and all these are related to each other. So the idea is very simple, that in the equivalence relations there is some kind of equality. here we have equality of shape. Okay, the shape must be same, then we can say that elements are related. So this element is related to this element, also this element is related to itself, this element is related to itself. So all these three elements are related to each other, all these two elements are related to each other, though these three elements are related to each other. So this is the idea of equivalence relation. You can also notice that the equivalence relation, what it does, okay, it will partition the set. Okay, this is our set is basically this. Okay, this complete thing, this is our set S, this is our set S. Now you can clearly see that our set S, okay, so this complete set, this is set S, and the equivalence relation has divided our set, has partitioned our set. Okay, so you can notice these three are in one part, these two are in one part, these three are in one part. So this is what equivalence relation does. Equivalence relation will partition the base set. Similarly, notice this another. Okay, so you can notice this is our set S. Okay, our set S is basically this, and this set S is partitioned into three parts using this equivalence relation. This is the equivalence relation. Okay, similarly, you can define another equivalence relation, and that is same color. X is related to Y if and only if X and Y have same color. So this type of relations are equivalence relation because there is some kind of equality here. Here we have equality of color. So what will happen? Okay, you can clearly see that. Okay, this is what will happen. So this is your set S. I can say this is your set S, and now this set S we are getting a partition. This equivalence relation has partitioned our set S into some parts. Okay, in this part you have these three elements, in this part you have these two elements. These three elements we have in this part. Why? Because they are related to each other, they have same color. These two elements are in this part because they have same color. These two elements are in this part because they have same color. This element is in this part because this has, okay, this has a different color from all other. So this is the idea of equivalence relation. So equivalence relation is reflexive, symmetric, transitive, and in the equivalence relation there is some kind of equality. Okay, equality of value, equality of color, equality of remainder, some kind of equality. And also the equivalence relation will divide our base set into partition. Okay, will partition our base set. Now the next terminology in the equivalence relations, remember the equivalence relations are very 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 important. Okay, so in the equivalence relations, if A is related to B, okay, then we say that A comma B are equivalent. Then this is what we say. Okay, because remember this equivalence relation is reflexive. So if A is related to B, then what will happen? Then automatically B is related to A. Okay, if this will happen, then definitely this will happen because equivalence relation is symmetric. Okay, so I can say that if A is related to B, then this is what we will say. We will say A is equivalent to B, or I can say B is equivalent to A because the equivalence relation is symmetric. So this is the idea. So we can say that two elements are equivalent. If they are related, then we will say that they are equivalent in the equivalence relation. This terminology we only define for equivalence relation. Also, if you have some element, let's assume you have a set A, and on this set A, you are defining a relation R on set A. If this relation R is equivalence relation, let's assume if this is equivalence relation, then what we can do, this equivalence relation will divide our set into partition, will divide our set into some parts. Okay, now here we have something called, what is the equivalence class of A? What is equivalence class of A? What is this? This means equivalence class of A. So for any element, okay, for any element in our base set, this is our base set on which we are defining equivalence relation. This relation R is equivalence relation. Then what this symbol means? This symbol basically means that this is the equivalence class of element A. Element A is in our base set. So this is the equivalence class of element A with respect to R. What is this? This is set of all elements, okay, to which A is related. This is set of all elements to which A is related. So this is the idea. So I can say that for any element, okay, remember you have equivalence relation, you have equivalence relation R on set A, and let's assume you have any element. Okay, whatever element you want you can take. Okay, so for any element in the base set, what I can say, this is equivalence class of A, equivalence class of A with respect to R. This is basically set of all elements to which A is related, to which A is related. And remember, equivalence relation is symmetric. So I can also say that this equivalence class of A, that is basically set of all elements which are related to A. Both these things are same. Okay, so this is how you can do. This is the idea. This is the concept of equivalence class of an element. Okay, so if R is equivalence relation on set A, then for any element in this set A, we can define equivalence class of that element, and that will be those elements which are equivalent to A. I can simply say, because if A is related to Y, then I can simply say that A is equivalent to Y. Okay, so I can say that basically this, I can say equivalence class of A, that is basically all those elements which are equivalent to A. All those elements which are equivalent to A. Okay, so all those elements which are equivalent to A. So this is the definition of equivalence class of element A. Remember, this symbol means equivalence class of A. So basically this means equivalence class of A with respect to this relation R. This relation R must be equivalence relation. Okay, now let's take this example. So this is your base set. On this base set you are defining this relation. Tell me, is this relation equivalence relation? Check. So you need to check reflexive, symmetric, transitive property. So clearly this is reflexive. Okay, because every element is related to itself, so this is a reflexive. This is symmetric also, this is transitive also. This relation is basically called identity relation. This relation is known as identity relation, and this identity relation, this is reflexive, symmetric, transitive. So definitely this is equivalence relation. I can say this is equivalence relation. If this is equivalence relation, then what is the equivalence class of 0? What is the equivalence class of 0? Equivalence class of 0 means those elements, it means those elements which are equivalent to 0. Those elements which are equivalent to 0. Or I can say those elements to which 0 is related. Okay, so this is the idea. So which are those elements to which 0 is related? 0 is only related to 0. So here I can say the equivalence class of 0, that will be basically 0 only. Similarly, the equivalence class of 1 means those elements to which 1 is related to. 1 is only related to 1. So the equivalence class of 1 is 1. The equivalence class of 2 will be only 2 because 2 is related to 2 only. Okay, and similarly the equivalence class of 3, that will be basically 3. So this is the idea. Okay, now these are the equivalence classes. Now I can say that what is this? If you notice, this is basically the partition of our set. So this is our base set. So I can say that this is basically partition of base set. This is partition of base set. Okay, so the equivalence relation, what it will do? This equivalence relation will do the partition of our base set. Each equivalence class is basically a part of this partition. Okay, so this is how you can check. Now let's take this example. Is the following relation equivalence relation? So 0 is related to 0, but you can notice 1 is not related to 1. So this is not reflexive. Definitely this is not reflexive. Because this is not reflexive, so this is not equivalence relation. This is not equivalence relation. What about next? This one. Is this equivalence relation? 0 0 1 1 2 2 3 3. Okay, 1 2 2 1. So is this equivalence relation? You can clearly check that this is reflexive. This relation is reflexive. This is also symmetric, and this is also transitive. Okay, so all these three properties are satisfied. So this relation is definitely equivalence relation. And if this is equivalence relation, then what is the equivalence class of 0? Okay, so tell me, what is the equivalence class of 0? Equivalence class of 0 means all those elements to which 0 is related. 0 is only related to 0. So this is the equivalence class of 0. What is the equivalence class of 1 with respect to this relation? What is the equivalence class of 1? Equivalence class of 1 means those elements to which 1 is related. 1 is related to 1, also 1 is related to 2. Okay, 1 is related to 1, 1 is related to 2. You can notice this is also the equivalence class of 2. Okay, this is equivalence class of 1, this is also equivalence class of 2, because equivalence relation is transitive, symmetric, and reflexive. So because of this property, basically because of this symmetric and reflexive and transitive, because these three properties, I can say that, okay, this for this one, this is the equivalence class of 1, this is also equivalence class of 2. And what is the equivalence class of 3? Equivalence class of 3, that basically means those elements to which 3 is related. 3 is only related to 3. Okay, so this is the equivalence class of 3. So how many equivalence classes we have? You can clearly see that only these equivalence classes we have. Okay, so uh, we have these equivalence classes. We have this equivalence class, this equivalence class, and this equivalence class. So total 3 equivalence classes we have. These are the total equivalence classes. You can notice this is also partition of our base set. This is partition of a base set, because this is the set on which equivalence relation is defined. So this is partition of our base set. Okay, these equivalence classes. we have only three equivalence classes, and these three equivalence classes, these are basically, they create partition of the base set. Each equivalence class is a part of partition, so this is called equivalence class. You can call it a equivalence class, and also this is a part of partition. I can say this is part of partition. Okay, so this is the idea. Now let's see the next one. Is this equivalence relation 0 0 1 1 2 2, okay, 3 3, and you can notice. So first you check, this is definitely symmetric, this is symmetric, this is reflexive, but is this relation transitive? Just check, is it transitive? So for transitive, what you can do, you can create the graph and you can check it out. So the graph you can create like this. To check for transitivity, the best method is graph. You can create the graph like this. So okay, 0 0, so there is 0 0, 1 is related to 1, 2 related to 2, 3 related to, okay, so 3 related to 3. So this is the idea. Now you can notice 1 related to 3, okay, and you can notice 3 related to 1. Next, 2 related to 2, 2 related to 3, 2 is related to 3, and 3 is related to 2. Okay, 3 is related to 1. Okay, so 2 related to 3, 3 related to 2. Okay, so this is the idea. Now is this transitive? Check, is this transitive? This is not transitive. This is not transitive. Why this is not transitive? Because you can notice 2 is related to 3, 3 is related to 1, but 2 is not related to 1. This edge is missing. Because of this, I can say this is not transitive, because you can clearly see that 3 is that 2 is related to 3, 2 is related to 3, 3 is related to 1, but you can notice 2 is not related to 1. Okay, so that's the reason this is not transitive, and hence I can say this is not equivalence relation. This relation is not equivalence. What about this? Okay, this is a relation that is given to you using the graph representation. This is the graph representation of a relation. Is this equivalence relation? This is also not a equivalence relation because this is not transitive. You can clearly check, this is symmetric, this is reflexive, this is symmetric. Okay, this is reflexive because all the self loops are there. B is related to B, D is related to D, so all the self loops we have, so this is reflexive. This is also symmetric, okay, because if A is related to D, so D is also related to A. So basically all the arrows are bidirectional arrows, so I can say this is symmetric also. But this is not transitive. Why this is not transitive? Because you can notice D is related to A is related to C, but D is not related to C. So this edge is missing. Okay, so I can say that D is related to A is related to C, but I can say that D is not related to C. So that's the reason this is not transitive. Hence, this is not an equivalence relation. Next, is this equivalence relation? Again the same thing. This is also reflexive symmetric, this is reflexive, this is also symmetric, but again this is not transitive. Why this is not transitive? You can check, this arrow is missing. For example, D is related to C, C is related to B, but I can see that D is not related to B. Okay, so that's the reason this is not transitive. Hence this is not equivalence relation. Okay, now let's move on. Let's see this example. Let R be a relation on set of integers, okay, such that A is related to B if and only if A is equal to B or A is equal to minus B. Is this equivalence relation? You can pause the video and you can think about it. So relation R, that is basically from integers to integers, because the relation R you are defining on set of integers. So integers are related to integers, and the question is saying that A is related to B if and only if A is equal to B or A is equal to minus B. What this basically says, this basically says that on set of integers, your base set is set of integers. So this simply says that 2 is related to 2. Also it says 2 is related to minus 2, minus 2 is related to 2, and minus 2 is related to minus 2. So this is what this relation is saying. A is related to B if and only if either A is equal to B or A is equal to minus B. So you can clearly see that these things will happen. 2 related to 2, 2 related to minus 2, minus 2 related to 2, minus 2 related to minus 2. So these things are happening. Okay, so basically I can say that A is related to B. Okay, what this means, this basically means, what this means, this basically means that the absolute value of A is equal to absolute value of B. Okay, so this relation I can say that A is related to B if and only if A comma B have same absolute value, have same absolute value. Absolute value means without sign. So remove the sign, remove this, okay, this remove this positive or negative sign, and then I can say A is related to B if and only if A comma B have same absolute value. And you already know this type of relation, A comma B have same absolute value. So there is some kind of equality here. In this relation we have some kind of equality, okay, the equality of absolute value. So this type of relation are normally, I can say, these are basically equivalence relation. You can check it out. This is definitely equivalence relation because this is reflexive. This relation is reflexive because you can clearly see that A is related to A. Why? Because A is equal to A. Similarly, this is symmetric also. This relation is symmetric because if A comma B have same absolute value, then definitely B comma A also have same absolute value. This relation is transitive also because if A comma B have same absolute value, B comma C have same absolute value, then I can say A and C they have a same absolute value. So I can say A is related to C. So this is transitive also. So all these three properties are satisfied. So I can say this relation is basically equivalence relation. This relation R, this is equivalence relation. Now, because this is equivalence relation, now what you do, you find the equivalence class of elements. So let's find out. So what is the equivalence class of 2? Because remember R is equivalence relation. Because this is equivalence relation, so what you can do, you can try to find out what are the equivalence classes of 2. So what is the equivalence class of 2? Equivalence class of 2 means those elements to which 2 is related. 2 is related to 2 by reflexivity. 2 is related to minus 2. So this is the equivalence class of 2. You can notice this is also the equivalence class of minus 2. Okay, so this is the idea. I can say 2 is equivalent to 2. I can also 2 is equivalent to minus 2. Okay, so this is the idea. 2 comma minus 2 they are equivalent because I told you that in the equivalence relation, this R is a equivalence relation. In the equivalence relation, if A is related to B, then we call them equivalent. So you can notice 2 is equivalent to minus 2 here. So the equivalence class of 2, this is the equivalence class of 2. This is also equivalence class of minus 2. What is the equivalence class of 0? The equivalence class of 0 will be basically only 0. Equivalence class of 0, that means what are the elements to which 0 is related? 0 is only related to 0. Okay, so you can clearly see for any integer, okay, actually for any integer other than 0, for any integer other than 0, this x should not be 0, x is not equal to 0. Okay, or I can say simply, I can say that for any integer what will happen, for any integer x, I can say what is the equivalence class of this integer. The equivalence class of this integer will be x comma minus x. You can check. Okay, this is correct. Why? Because for 0 what will happen, 0 comma minus 0, 0 comma minus 0 is same, so ultimately you will get 0. So this is the idea. For any integer, whatever integer you take, for any integer the equivalence class will be basically x comma minus x. For integer 2 the equivalence class is 2 comma minus 2. For integer 3, if I ask you what is the equivalence class of 3, then equivalence class of 3 will be 3 comma minus 3. This is the equivalence class of 3. So this is equivalence class of 3. Okay, so here in this question you can clearly see these are the equivalence classes. I can say, okay, so this is a equivalence class you got, this is another equivalence class you got, this is another equivalence class you got, this is another equivalence class you got, and so on. Like this you are getting the equivalence classes. What is this? Okay, if you notice all these equivalence classes, then what you are getting, this is a partition of the base set. This is a partition of base set. And what is the base set? You already know your base set is basically set of integers. So this is basically partition of set of integers. You can notice, okay, they are mutually disjoint. Okay, all of them are mutually disjoint. Oh, every integer is covered, every integer is in one of the partition, one of the part. Okay, so this is a part, this is a part, this is a part. I can say every integer is in one of the part, and these are mutually disjoint and none of them is empty. So definitely this is a partition of our base set. Okay, so you can notice that equivalence relation, because this relation R is equivalence relation, so equivalence relation will partition our base set. Our base set is Z. Okay, so the equivalence relation will partition our base set. Okay, the set of all the equivalence classes, remember this is a equivalence class, this is a equivalence class, all are equivalence classes. The set of all the equivalence classes, that is basically the partition of our base set. Okay, let's take another example. Let R be the relation on set of real numbers, and we are saying A is related to B if and only if A minus B is an integer. Then what can you say? A is related to B. Remember the okay. This is saying R is relation on set of real numbers. On set of real numbers. So here our base set, this real number, this okay. So your base set is basically set of real numbers. This is the base set. that is a set of all real numbers. This is the base set. Okay, so our relation R, if you notice, okay, so let me call this relation S, so that there is no confusion. So let me call this relation S. Now this relation S and this, let me call it A as B. Okay, so now you can notice this relation S, this is basically from real numbers to real numbers, because this relation S is defined on set of real number, and we are saying that X is A is related to B if and only if A minus B is integer. So just check, is this reflexive? Definitely this relation is reflexive, because for any real number A, okay, A minus A is definitely integer. This is definitely integer. So I can say for any real number, whatever real number A you take, what will happen? A is related to A, because A minus A is 0 and that is integer. Is this symmetric? Yes, this is symmetric also, because if A minus B is integer, if this is integer, then definitely B minus A is also integer. Then I can say B minus A is also integer. And what about transitive? What about transitive? This is transitive also, because if A minus B is integer, okay, B minus C is integer, then I can definitely say that A minus C is also integer. You can just check it out. Okay, so this is transitive also. This relation S on R, real number, this relation S on real numbers, you can notice this relation S is basically equivalence relation. Because this is equivalence relation, so now we can find out the equivalence class of elements. So tell me, what is the equivalence class of 1? Okay, in this relation, the relation is S and this is equivalence relation. Now what is the equivalence class of 1? Equivalence class of 1 means those elements which are related to 1. Okay, so which elements are related to 1? You can notice that 1 is related to B. Okay, A is related to B if and only if A minus B is integer. So 1 is, okay, what is the equivalence class of 1? That is basically set of all integers. Okay, every integer will be in the equivalence class, because 1 is related to 1, 1 is related to 0, 1 is related to minus 1, 1 is related to minus 2, 2, minus 3, 3, 1 is related to every integer. So I can say the equivalence class of 1, the equivalence class of 1, that is basically set of all integers. This is also equivalence class of 2. This is also equivalence class of 3. Basically this is equivalence class of any integer. Okay, whatever integer you take, for any integer, this is the equivalence class, because you can notice that 1 is equivalent to b 1 is equivalent to 2. Why? Because 1 is related to 2. 1 is related to 2. Similarly, you can notice 1 is related to minus 2, so I can say 1 is equivalent to minus 2. Okay, so this is equivalence class of 1, this is also equivalence class of 2, this is also equivalence class of minus 1, this is also equivalence class of 0. So equivalence class of any integer, whatever integer you take, for any integer, equivalence class will be set of all integers. Okay, and similarly you can find out, for example, if I ask you what is the equivalence class of 0.5, because our base set is set of real numbers, okay, and our relation is S. So what is the equivalence class of 0.5? Equivalence class of 0.5 will be basically this type of number, x.5, this type of numbers where x is integer. Okay, where x should be integer. So this type of elements are in the equivalence class of 0.5. Okay, so this is the equivalence class of 0.5. Okay, so this is the simple idea, I can say. This is also equivalence class of 3.5. This is also equivalence class of minus 3.5. Okay, so this is the simple idea, that what is the equivalence class? What is the equivalence class of an element? Because S is equivalence relation on this set of real numbers, so I can find out, okay, what is the equivalence class of any element. Okay, what is the equivalence class of 1? What is the equivalence class of 0.5? So what is that? Okay, so this we can find it out. Now let's see the next example. This is congruence modulo 3. Okay, and this is saying that you have a relation on set of integers. We have a relation and we are saying A is related to B if and only if they give the same remainder when you divide by 3. Okay, so basically this means A is congruent to B modulo 3. Okay, so what this means? A is congruent to B modulo 3. This means that 3 divides A minus B. Okay, or I can say, basically I can say that A comma B, they will give you same remainder when you divide by 3. Is this equivalence relation? Yes, definitely this is equivalence relation, because what this means, so this is saying that A is related to B if and only if A comma B have same remainder when you divide by 3. So this type of relations are normally equivalence relation. I told you, you can check it out. This is reflexive, symmetric, transitive. This we have already done in the class. So anyway, this is reflexive, because definitely A 3 will divide A minus A. Okay, So this is the idea. This is symmetric, and also this is a transitive. So this is the equivalence relation. Because this is equivalence relation, so you can find out what are the equivalence classes of 0 comma 1. So what is the equivalence class of 0? Equivalence class of 0 means those elements, okay, to which 0 is related, or I can say those elements which are related to 0, because equivalence relation is symmetric. So okay, so both are correct, both of these are correct. So I can say what is the equivalence class of 0? Equivalence class of 0 will be, it will be 0. So basically those elements you will have which will give you same remainder when you divide by, okay, so this 0 will give you remainder 0. So okay, this 0 is equivalent to, I can say this 0 is equivalent to 3, because both of them will give you remainder 0. Okay, 0 is equivalent to 6, both of them will give you remainder 0. 0 is equivalent to minus 3, both of them will give you remainder 0. So this is the idea. Okay, so this 0, this is equivalent to 3, this is equivalent to minus 3, this is equivalent to 6, this is equivalent to minus 6, okay, and so on. This is the idea. So this is the equivalence class of 0. So equivalence class of 0 has all those elements which are equivalent to 0, or I can say has all those elements which are related to 0. You can notice 3 is related to 0 because 3 comma 0 will give you same remainder when you divide by 3. 6 is related to 0 because 6 comma 0 will give you same remainder when you divide by 3. 0 is related to minus 3 because they will give you same remainder when you divide by 3. So I can say this is the equivalence class of 0. In this equivalence class of 0, basically, okay, I can say that this is 3k where k is integer. Where k is integer. This is the equivalence class of 0. What is the equivalence class of 1? Equivalence class of 1 means those elements which are related to 1. Okay, I can say which are equivalent to 1. So you can notice 1 is equivalent to 4 because they will give you same remainder when you divide by 3. 1 is equivalent to 7, they will give you same remainder when you divide by 3. 1 is equivalent to 10, they will give you same remainder when you divide by 3. 1 is also equivalent to minus 2 because they will give you same remainder again when you divide by 3. Okay, so anyway, this is the simple idea. So I can say the equivalence class of 1, that is basically I can say that is 1 is related to 1 by symmetry, sorry, by reflexive property. 1 is related to 1. 1 is also related to 4, 7, minus 2, minus 5, okay, and so on. So these are the elements to which 1 is related. So what is the equivalence class of 1? Equivalence class of 1 is basically 3k plus 1 where k is integer. Okay, means those elements, set of those elements which will give you remainder 1 when you divide by 3. This is the equivalence class of 1. And similarly, finally, I can say what the equivalence class of 2. Equivalence class of 2 will have those elements which will give you remainder 2 when you divide by 3. Okay, so like these elements, i can say I can say these elements you have in this okay, in this equivalence class. So this is the equivalence class of 2. So you can clearly see how many equivalence classes you have. Here you have 3 equivalence classes. Okay, this is one equivalent. I can say that what is this equivalence class? This is basically 3k plus 2 where k is integer. Okay, so here I can say that these 3 equivalence classes you have. One equivalence class you have this, okay, where k is integer. This is one equivalence class. Basically in this you have all the integers which are divisible by 3. And another equivalence class you have this. In this you have all the integers which will give you remainder 1 when you divide by 3. And in this you have all the integers which will give you remainder 2 when you divide by 3. So this is a partition of our base set. Our base set is set of integers. So I can say this is partition of the base set. You can clearly see. Okay, because these are mutually disjoint and they are non-empty, and also they cover all the integers. Every integer is covered. So for the base set, I can say this relation will partition our base set into 3 parts. So there will be 3 equivalence classes. We have 3 equivalence classes for this relation, and these are the equivalence classes. So the idea is this: every equivalence class is basically part of the partition. Okay, so remember, we have 3 equivalence classes. These are the 3 equivalence classes for the relation. Okay, so these are some examples of the equivalence relation, and in the next lecture we will take some more examples. This equivalence relation is very important. That is the reason we have taken a lot of examples, a lot of variations we have taken. In the next video we will take some more examples, and this is extremely important. This topic is extremely important, so understand this carefully. Okay, thank you.